everyone. My name is Ashley. I'm a second-year BME pre-med, and I'm from the Grossberg lab. I'd like to start this presentation by dedicating it to my grandfather. Since I was a young girl, I watched him undergo various treatments and surgeries for his cardiac issues. And unfortunately, last week, we lost his life to a cardiac arrest. But this is not an isolated scenario with just my grandfather's story. Cardiovascular diseases are a leading cause of death worldwide. And while cardiovascular diseases can be studied through a variety of models like animal studies and patient observations, these methods fall short because they can't isolate specific cellular mechanisms. And this is important with cardiovascular diseases because cardiovascular diseases are extremely complex, and a lot of factors play into them. So having a model through which we can isolate specific cellular mechanisms can play a key role in finding advancements. And that's exactly what the heart on a chip does. The heart on a chip is a 5-layer model through which we engineer heart muscles, and we can assess how they form and how they beat through this model. My project specifically focuses on the elastic polymer layer. The elastic polymer layer is made of something called PDMS, which is a silicone substrate that mimics the soft and flexible nature of our muscles. Now, in order to make this layer, we coat a layer of PDMS on glass. But in order for this layer to be functional, we need this layer to be free of air bubbles and even. But you can see that initially we were facing an issue because visually you can see air bubbles on this layer. And if you look at the range of thicknesses amongst the layer, it ranges from 5 to almost 15, which is a range of 10. And having an uneven layer like this is not good for the model because an uneven layer means the cells won't adhere to this model, meaning they won't beat, meaning we can't assess them. And we hypothesized that the reason for this was moisture contamination. And in order to address this, we decided to place our solution in an oven, a 60-degree oven, with vacuum desiccators in hopes that all the moisture from the PDMS solution gets drained out before we coat it on our glass. And the results were that visually, we could no longer see any air bubbles. And if you looked at our thicknesses, the initial range of 10 dropped from 1 to 2 to 4, which is a significant improvement. And having a more even layer free of air bubbles meant better experimental reliability because this meant that the cells stuck to the model better, meaning they beat better, meaning we could experiment with them better. And while this project has been going in a positive direction, it is far from over, and we're still working to make it more consistent so that we can have a reliable model that is controlled and can assess specific mechanisms and play a key role in advancing treatments for cardiovascular diseases. Thank you.